Hey there, Duckonta here. Today we're going to talk about real-world solutions. By the end of the video, hopefully you will be able to explain and apply these chemical terms and how solutions are important in your daily life at home, including on the news, like Flint, Michigan, or what's happening in Newark, New Jersey today. Let's go over what we're going to talk about today. The first thing we're going to talk about is, well, in order to discuss these chemical terms with you, we got to be on the same level in knowing what these words mean. So I want to give you a little bit of background on what solution terms are, what they mean, and what you should know about it. Then I'm going to give you some application, so in that Flint, Michigan aspect of understanding what happened in Flint, Michigan, what actually went down within those years. And the ongoing issues that we are now seeing take place in Newark, New Jersey, in the politics thereof, how we're handling this drinking water, what lead poisoning can do to an individual and why it's so dangerous, some misconception, well, one particular misconception that I think is kind of big out there, I've heard often from students, and last but not least, and most importantly, how on earth are we going to fix this problem using chemistry? So let's apply everything that we've learned from before, those words, those terms, and then how could we fix this in the real world? What's going on chemically here? All right. So for those of you that aren't maybe so map inclined like I wasn't, I thought that Arizona was America for the majority of my preteen life. So definitely check out this map over here, Flint, Michigan, up in that northern corner of the United States, more on the East Coast side. In that region is where we're kind of going to be focusing our efforts, and along the East Coast where there's a lot of older homes. By the way, if you haven't seen my previous lesson yet on home water testing, the kind of backdrop for this information, please click on the link below that I've added for that home water test video and the whole kind of reason why we're learning this and the whole backdrop of this here. All right. So first and foremost, what is a solution? I'm not talking about like just the solution in math. No, right? Math is the bane of our existence. Ooh, scary math. Solution is when you take something, right? So if we're just looking at this picture, we got like Kool-Aid. Oh yeah, right? We got Kool-Aid man, and we put Kool-Aid in water. Ooh, scary water, right? We make Kool-Aid. Great. The Kool-Aid itself in the picture over there is the solution. So in this picture here, what we can see then is that the Kool-Aid right above me, this powder, is what we refer to as a solute. Solute. The thing, oh, well, I'm getting used to this pointing thing here still. All right, so that water pitcher would be the solvent. Solvent. So we have a solute in a solvent, and when we add those two together, we make a solution. Our nice, cool, crisp drink of Kool-Aid on a hot summer day, right? So what I want to get down here is that a solution is a mixture of the Kool-Aid, i.e. the solute, and a solvent, i.e. the water. Could be a different liquid, but most of the time it happens to be water. So in this case, we can define a solute as the thing that gets dissolved. Now, if you are unsure of what it means to dissolve, what is dissolving, please go to my previous video about how and what items dissolve in what, and what does dissolving even mean to begin with. Please click on that link as well if you need some help with dissolving or the term dissolved. So again, solute is the thing that gets dissolved. Solvent is the pure liquid that does the dissolving. So it's the active participant in like pulling apart the parts of the solute to dissolve it, to break it apart. So again, right, we've got solute, solvent, solution. You think you can do it? I'm gonna test you. All right, there you go. So I'm gonna give you a second. You might want to pause the video at this point and just test yourself. Do you have those 3 words down? Give it a shot. I'll wait. All right, I can't wait that long. I'm not that patient. Okay, so hopefully you paused it and you said, hey, that is the solute, and let's see if I can get it right. Am I going to point the right way? Oh yeah, all right. And that is the solvent, and all the way at the end, that's our solution. Solute, solvent, Solution. Perfect. So we need a solute and a solvent to make a solution. Great. So then let's try and identify these just really quickly here. Try and entertain me, right? So if you're at home alone, especially, I encourage you to just like shout out these words, because why not? Live a little. Have fun, right? YOLO. So I want you to think, okay, would the image that I have depicted above, depicted above, would that be representing a solute, a solvent, or a solution? So I kind of want you to test yourself here. Alrighty. So lemonade powder, does it get dissolved or does it do the dissolving? Or is it already dissolved in something else? Well, hopefully you said that it gets dissolved because you need to add it to water in order to make lemonade. So that would make the country time lemonade powder a solute. All right, let's check this one out. Oh, so pitcher of water. Shout it out. Don't be shy. I mean, I can't hear you, but I mean, you know, right? Okay. That should be a solvent. That water pitcher is a solvent. Now, if we take those two together, we have full-blown lemonade, right? We've got our full-blown simply lemonade over there. That would be our solution all together. How about this one? Ooh, Jamaica. If you haven't had that before, seriously, treat yourself. It's really good. Hibiscus flowers, so tasty. Lovely, lovely, cool drink. Okay? That's a powder, and you have to mix it in water in case you don't know what it is. That would make that a solute. Solute, very good. Okay. Coca-Cola. For those of you that are maybe not Coca-Cola drinkers, I can't stand the stuff, gives me massive tummy aches. So for Coca-Cola, there's a lot of stuff in there, right? There's water, there's acid, there's CO2 bubbles, right? To give it all that fizziness, that fizz that everyone likes. There's sugar, a crap ton of sugar, in fact, right? And a whole bunch of other stuff. So what would we give Coca-Cola? It can't be a solute because there's a lot of stuff already in there. And it is a liquid, so we do drink it. So it can't just be a solvent because it's not a pure thing that does the dissolving. So it's got to be a solution. So Coca-Cola is a solution to your problems. Just kidding. But coffee is, really. All right, so sugar. Sugar, again, typically in terms of like, I'm thinking like crystalline sugar, what you'd add to your baking mixes and things like that, your tea, your coffee. That gets dissolved, so shout it out. It should be a solute. I know you said solute. I know. Perfect. Good job. Excellent. All right, so acetone. Acetone over here. This acetone can is representing a pure liquid. There is nothing else in it except for acetone, the chemical of acetone. In this case, that would be a solvent. Good. I'm sure you said solvent. There's nothing else in it. It's not a mixture. It's a pure liquid. Therefore, it's a solvent. And in fact, acetone can dissolve a lot of other things like nail polish, right? That's one of the major things we use it for. So it is a solvent. Alrighty. How about Tums? I am definitely eating a lot of Tums lately, being that I'm pregnant and acid reflux. Oh my goodness, big deal. All right, so Tums. I ingest those so that they hopefully dissolve in my stomach acid and make it so that I can actually sleep at night. So Tums would be a solute. Good, good. See, I know you guys are rocking this. You're doing great. All right, how about nail polish? This one's a little tricky. If you're not sure how nail polish is made, it's pretty much got all these different pigment colors added to it, which are solutes. And it's in liquid form that you can put on your nails and make them look all fancy. Mine are not so fancy. But we would call that a mixture, right, of two things. So that would be a solution. So again, painting your nails is a solution to your woes. Absolutely. Oh, all right. So hopefully you've got those 3 words down pat at this point. So let's think about how we could use these words to change the flavor of a drink, something that we're all kind of familiar with here. If we wanted to, I don't know, have these original ingredients, our Kool-Aid, our solute, our water, our solvent, and then the whole mixed together as our solution, how could we change the intensity of that flavor? Like, let's say we wanted a really, really sweet, like just, oh, so sweet version of the solution. What would we have to do? Hopefully you're thinking about this and you're saying, well, I know as a kid at one point, I put in, I don't know, maybe like half the jug of Kool-Aid with just like barely a cup of water. And it was so sweet you almost passed out, right? You added a lot of solute with a very small amount of solvent, and that gave you a really intense drink flavor, right? Like just utterly sweet, unbearably sweet, right? Likewise, this is called concentration. So the concentration, how much of the solute we have versus a solvent or a solution. So how much of the solid thing did we mix into the liquid thing, essentially? And that can change the concentration of the drink or any solution in general, right? Doesn't have to necessarily be a drink, just as an example here. So if we're looking at these pictures that I've got on the slides, if we have the same amount of powder in either situation over a solvent, which would be like this water pitcher, right? Or all the way on the other side, I have a pitcher of lemonade. That's the solution. So concentration is a ratio, one thing over another, of the solute per solvent or the solute per solution. So we can use those interchangeably to kind of describe the concentration of a solution. Alrighty. So let's see, is it concentrated or not? If we have a ton of lemonade powder, a little tiny bit of water, a little tiny bit of our solvent, lots of solute, tiny little solvent, are we going to be concentrated or not concentrated? Hopefully you're saying that's really concentrated. That's the scenario I threw out before where it was like, utterly sweet, right? Too sweet. How about if we flip the scenario? And in this case, we have just a little tiny bit of solute, our powder. We have a lot of water. So you got like a whole pitcher of water and you just sprinkled in a pinch of the powder. Wouldn't really taste like lemonade yet, right? It'd probably taste like water because you wouldn't even be able to tell. That would mean that it's not concentrated. There's not a lot of solute in the amount of solvent that you have. That ratio would be pretty small, not concentrated. Let's throw some numbers in here because I know we all love numbers, right? So if instead we're looking at this in terms of grams and liters, right? So if we had a half a liter of solvent, all right? So hold on, I got like water right here, so you can kind of tell. That's 500 milliliters, which is equivalent to half a liter. So if I had this much water and I have 100 grams of a solute, would that be concentrated or not? Well, that might be hard to determine just on its own. Maybe if we have a comparison. How about if you had 100 liters, i.e. 200 of these jars filled to here with 0.5 grams of a solute? Would that be concentrated? No, of course not. 0.5 grams? My gosh, that's like tiny little amount on a scale. That would be like our version of having little tiny bit of powder in a lot of water. So if we use that as a comparison, the 100 grams of solute in half a liter would probably be concentrated, right? That's a lot of solute in just one of these. Kind of gives you a visual representation there of concentration. Okay, so if we were going to apply this then, we've got Diego and Mia. And both of these guys apparently don't know how to make Kool-Aid correctly. So if they took their drink from that same pitcher of Kool-Aid that we previously mixed, and somehow Diego has a lighter color in his cup. So they took the same juice, and now Diego has a lighter color. How did he make his color lighter than Mia's? What did he do to do that? Hopefully, you're thinking in terms of, well, if this is Mia's cup, maybe she only poured out this much. right? Maybe Diego only poured out this much too. But then what Diego did was he went over to the kitchen sink or to his filtered water, right? And he was like, hey, you know what? I want to add some more water to this. And as he added more water, you can see that the concentration or the color changed. So what we see then is a lighter color from before. It's not as concentrated. Now there is more solvent per the same amount of solute that was present in the class. Alrighty. So what I just showed you is a dilution. I diluted something that was very concentrated. When we have something that's very concentrated, i.e. a lot of solute in a small amount of solvent, like what I started with in the cup, very small amount, and then I added more volume of solvent, the water, that decreases the concentration. So now I have less of a concentrated or more tolerable to drink, presumably, drink. I could also do this same thing if I had started with all the water in here and just added a tiny little bit of Kool-Aid, so less solute per the amount of solvent present. Alrighty, go ahead and give this a try. Let's look at this picture here. Notice that color is an indicator for concentration or dilution if something is more dilute. Also indicating how much solute is present, how many pieces or particles or parts on a molecular level or on an atomic level there are present per solvent. So if you notice there, we have solute particle and solvent particles. And if we look at our dilute and concentrated beakers, we can see that there are more solute particles than there are solvent particles, that ratio we were talking about in the concentrated beaker, than there are in the dilute beaker. Hopefully this gives you a visual representation before we apply all this stuff. So remember the end goal is we're applying this to Flint, Michigan, why this is important. Go ahead and quiz yourself here real quick. Which one has the highest concentration? Pause the video if you need to. I'll wait. But you know I'm not patient, so I can't wait long. The highest concentration is the one with the most solute. In this case, A, B, and C have the same amount of solvent. Notice they all have 50 milliliters across the board. The one that wins the prize for concentration is the one with more solute. In this case, that would be option B. There are more parts or particles or pieces that are there. Alrighty. So then how are these solutions made? These solutions can be made by mixing a solid and a liquid together, in which case you have a solution. Now remember that solubility ties into whether or not a solid will dissolve. Again, if you haven't refreshed yourself on the previous video on solubility and insoluble and soluble, what those words mean, please do click on the link and educate yourself there as well so that you can keep following along here. So, in order for something to dissolve in a liquid, it needs to be soluble. And if it does dissolve, then it is soluble in this case. So that's one way we can make a solution, is by putting a soluble solid into a liquid. And if it does dissolve, we get a solution. Another way we can make solutions are if we take two liquids together, so two different liquids, and then they mix together. This is called miscibility. I know it's like maybe they couldn't say mixability. They had to make it special, right? Miscibility. So this is the ability to take two liquids as opposed to a solid and a liquid and mix them together, right? So if you've ever made salad dressing, you know that you can typically put vinegar and water and you mix it together, right? To make your nice vinegary salad dressing. Those would be two liquids that you mix together to make a solution or to make a diluted version of the vinegar. So you're not like, right, the whole time you eat the salad. So sometimes in chemistry, what we see is that when two liquids come together, we actually get a spontaneous dropout of a solid. What? So literally envision two liquids. So I don't know if you're going to be able to see this, but if I took this liquid and this liquid, let's assume they were two completely different chemicals, and I mixed them together, boom, there'd be like something solid that comes out of it. A chemical reaction occurs, and we get an insoluble precipitate is what it's called. So something that is coming from two liquids that is no longer soluble within those two liquids in the new solution they form would then be called a precipitate. I know this is kind of a confusing topic, especially if you've never seen a precipitate before. So let's go ahead and try that. Let's see what it looks like. Oh, and thank you. Thank you for making this video. Totally awesome that you did. Big help for those of us that can't have these chemicals at home or play with them because we're pregnant, right? All right, so we can convince soluble chemicals into becoming insoluble. We can make solids. Now, this is a big deal because this is going to apply directly to Flint, Michigan. So please watch this video.
Solutions containing lead-2 ions are usually colorless. To test for the presence of lead-2 ions, we may employ the sodium hydroxide test. To a small sample of the solution, add a few drops of sodium hydroxide. Immediately, a white precipitate forms. Notice how the white precipitate dissolves in excess sodium hydroxide.
All right, so basically what he was showing us there is that we can take a clear liquid, a clear solution, right? There is no way, okay, let's backtrack here. There is no way that you could tell me in this test tube, hold on, we're gonna get that on the frame there, that in this test tube where you saw a clear liquid, right, that you could tell me that that's any different from this liquid. If you were to look at them side by side, you wouldn't know the difference. So in that test tube that he's holding, there are lead ions. Now, the term ions we haven't gone over yet, but it basically means that there's lead that's a solute that's been dissolved in that solution. So there's a solution of lead ions in there. And it looks identical to normal water. It doesn't smell funny. It doesn't have a different taste. You can't tell that there's lead in there. The only way we could tell is that he put in another solution. He put in sodium hydroxide, and that made the lead from being soluble, floating around in that water, in that solution, and caused it to become insoluble. It made it a solid spontaneously. Then we call that solid a precipitate. So that white stuff that kind of crashed out of the solution, as we like to say, that's the precipitate. And that was lead inside that precipitate. So it was coming out of the solution. It was like forcing all the little lead solutes that had dissolved before to be pulled out of the solution and form into a solid instead. So let's see why this is so important in terms of Flint. But first and foremost, what the heck happened in Flint? So what I want you guys to really think about while I play this video is, how did the lead get into the water supply? So CNN does a pretty good breakdown here, and they claimed, so these city officials claimed they didn't have to add what to the water? What is it that we're looking for? There's a word there that I really want you to listen for. Some kind of agent. And then, on top of it, what did the city recommend that made matters even worse for the Flint, Michigan citizens? I'm going to kind of disappear so you guys can watch the video. So. Toodles.
Melissa Mays says the ominous change in the water was particularly noticeable at bath times.
My youngest would tell me, Mom, it's yellow and it's a filmy, gross, foamy thing, and it would smell like open sewer. But we were being told we're still getting used to the new system. It's safe, it's okay.
But it wasn't okay. Far from it. Flint's tap water was laced with dangerous levels of lead. The state knew about it and did nothing.
The trouble began 2 years ago when the state decided to switch Flint from Detroit's drinking water to a new system. But the new system wouldn't be ready for 2 years. In the meantime, to save money, they switched to the Flint River water.
3, 2, 1.
That first decision turned out to be a mistake, as did nearly every step the state took after it. Michigan's Department of Environmental Quality shoulders much of the blame, what a preliminary task force report calls an abysmal public response. At the time, the state agency told Flint it didn't have to add an anti-corrosive agent to the water, saying it was not necessary until 2 6-month monitoring periods had been conducted. In other words, they were willing to wait a year to see whether the water was safe. All the while, highly corrosive river water flowed through the city's lead pipes, leaching lead and other dangerous metals into the water supply, and what came out of the tap in many homes was toxic. Almost immediately, residents started complaining. Their water was brown. Some people developed rashes, became sick. Early tests revealed fecal coliform bacteria. So the city and state officials added chlorine to the water supply and told people to boil their water. Both mistakes which can actually increase the level of lead.
I built this place with my tax money.
At city meetings, residents were repeatedly told the water was safe.
We found the worst lead and water contamination that I have seen in 25 years, and believe me, I've seen a lot.
Residents didn't find out about the lead until this man stepped in. Mark Edwards is a Virginia Tech researcher who tested the water early last year.
It was very scary to see the levels of lead that were hazardous waste levels of lead coming out of her tap water.
That's right. The lead levels in one home were so high, water from the tap could be considered hazardous waste. His testing led to this EPA memo, an interim report which was leaked last summer. It said the high levels of lead in the water were especially alarming because the state's water testing was flawed, so the true lead levels were probably much higher.
We were just waiting for the appropriate authorities to help Flint residents to enforce federal law.
When Flint's former mayor asked the EPA for more information, he was shot down, as you can see in this email exchange obtained by CNN. The EPA regional director writes, "The preliminary draft report should not have been released outside the agency, and that only when the report is revised and fully vetted will it be shared with the city." But that wouldn't happen until months later. Meanwhile, families were still drinking water poisoned with lead. The EPA blames the state, saying in a statement to CNN, what happened in Flint should not have happened, and that the EPA's ability to oversee was impacted by failures and resistance at the state and local levels. The state was continuing with its own mistakes, according to Mark Edwards, butchering around a water testing. They not only tested the wrong homes, but altered the reports, eliminating tests from 2 homes that would have shown toxic levels of lead. The state says the changes were legitimate.
They fabricated a report that made it appear like Flint was passing the lead and copper rule with flying colors.
In the fall, the government admitted that there was lead in the water and Flint was switched back to Detroit's water supply. But it wasn't until earlier this month that the state of Michigan started bringing in bottled water and declared a state of emergency.
All right, so not so good, right? Hopefully that's what you got from that. How did the lead get in the water supply? Well, just to clarify, it got in because of their negligence. They weren't treating the water, they switched the water source, and then the water was basically creating this corrosive property in the old pipes that are underground in Flint, Michigan, causing lead to enter into people's home water. They claimed they didn't have to add an anti-corrosive agent to the water. They said it was fine the way it was, even though pretty much most water treatment facilities use an anti-corrosive agent to ensure that this doesn't happen. And then, on top of it, to make matters worse, they were like, hey, let's add some chlorine to cover up that poop matter, if you didn't catch that, the fecal coliform. Yeah, they wanted to, eliminate that bacteria. And so they said, hey, and then boil it before you drink it. Oh boy. When you boil it, think about it. We've been talking about solutes, solvents, and solutions. If you have a solution with lead in it, and you boil the water, do you think that the solute of lead boils out of the water? Or do you think it stays in the water? Well, let me ask you this. If you boil a metal, does it take a lot of heat to get most metals to melt? Like if you wanted to melt a penny or a nickel or anything else made out of metal, maybe like a pair of scissors, if I wanted to melt the metal, would that take a substantial amount of energy, you think? Maybe more than what your stovetop could provide, or more than the temperature of boiling water would get to? Exactly. So what happened is they were boiling away the solvent, they were decreasing the solvent in a solution, and increasing the solute, still present, the lead. I.e., they were increasing the concentration of lead within the water they were drinking. So essentially, the Flint, Michigan City Council advised all of these people to poison themselves even worse with more concentrated lead water. Awesome. Alrighty, so moving right along here. Breaking news, this isn't just a Flint, Michigan problem. By the way, that happened, this whole thing began in like 2014 for Flint, Michigan. The dangerous levels were declared in 2015, and then it hasn't been until 2018 that the free bottled water program was stopped and they declared that the water was safe to drink again. But of course, most of the residents are like, we don't really trust you guys anymore. I don't know if I want to drink my water. So they've actually seen a lot of decrease in the water consumption just because people don't trust it anymore. I can't blame them. Anyways, so now breaking news. This is just happening recently. As you can see, I pulled this today, and today is October 11th, 2019. So 1 day ago, 16 hours ago, 1 day ago, high levels of lead found in Newark. So we're talking New Jersey here now. Again, along the East Coast, we're seeing these same issues arise. This hasn't been just like a out of the blue thing either. In 2016, this is coming from the New York Times, by the way. Link is posted right there on the bottom if you want to check it out. In 2016, they were saying, hey, we had to shut off 30 schools' water fountains because they had elevated lead levels. That was 3 years ago, guys. Alrighty, so now they're like, hey, in 2017, January, they're like, alright, well, check out these tests where 10% of Newark's homes had water lead levels nearly twice the federal standard. Now, if you recall from my last video, the home water testing, the federal standard for lead is 15 parts per billion, or 0.015 parts per million. So less than a part per million is what the EPA considers okay. And even that is, in my opinion, a little bit much. I mean, there's no level of lead that is safe, guys. Lead is very dangerous, all right? So twice the federal standard. Yikes. Ay chihuahua. All right. Now, in July 2019, a test showed that Newark's water had lead levels at 55 parts per billion. Whew! Again, the max level was 15. 1-5. And now they're saying, hey, there's a few homes that are showing 55 parts per billion. This is a big problem, guys. This is a big issue. Side note here, you might have caught in the video that I showed you earlier from CNN that they had mentioned the lead and copper rule. This is a rule that was established in 1991 that replaced a previous rule that said, hey, the EPA max level should be 50 parts per billion. In which case they were like, I think that seems like a little bit much, guys. And so in 1991, they brought that down to that 15 parts per billion, which is way more reasonable. I mean, really, it should be none, but it's reasonable, okay? Better than 50. And this rule that we currently have states that, hey, if we do end up finding any kind of service lines or a home that has water testing with above 15 parts per billion or around there, right, or around their action level, that they need to start replacing the pipes or the lead service lines that are underground, and there has to be 7% of those done within a year's time. This has been kind of a rule that hasn't been updated for a really long time. So now what we're seeing actually as of today, right now, October 2019, is that they're saying, hey, we need to update this, we need to revise this. So the current update is that they're going to require water systems with lead above 15 parts per billion to replace 3% of their lead service lines right up to the individual homes. So we're not just talking like the underground pipes that are leading, you know, just the main ones. We're also talking now the pipes that go to individual homes that branch off the main ones directly up to individual homes. But notice they've also changed the percentage that needs to be done within a year's time. So 3%, much less than before, of 7%. So in my opinion, if you want to talk politics, this is sort of a compromise issue. They said, hey, it's really hard to rip up the ground to replace these pipes. So what we're going to do is we're going to also have a trigger level of 10 parts per billion. So if we see any homes that come back as 10 parts per billion, that's kind of like our trigger to start doing something now, our kick in the pants, like let's go out there and start digging now. Make sure we can take preventative action before it gets to 15 parts per billion or higher. So basically what this new amendment to the lead and copper rule is that they're going to take longer to replace the lead pipes, but they're going to do it right. So it sounds anyhow. They're going to replace it all the way up to homes, within home fixtures and things like that to make sure that the lead is completely wiped out, including any kind of connectors to the pipes, is what I have read, what I'm assuming they're trying to do. But of course, this raises a lot of concern because this would lengthen the amount of time that lead pipes are present, since they should have been replacing them 7% of them within a year, and now it's dropped down to 3% of the lead pipes to be replaced within a year. Okay, so politics aside, let's get back to the chemistry here. So for lead poisoning, according to the CDC, the Center for Disease Control, even short-term exposure of lead can have catastrophic effects, particularly for pregnant women, for developing babies, obviously, and for children, especially. But adults can also experience memory loss, abdominal pain, cramping, weakness, pain, tingling, tiredness, headaches, you name it. You've got a whole myriad of medical issues that you could deal with here with just a small amount of lead exposure. Short-term exposure even. So kind of a big deal. Not something you really want to mess around with. Another thing to note about lead poisoning is that, as I mentioned before, you can't tell if there's lead in the water. The only way you can tell is if you do a chemical test through a lab, or you test your water yourself with a home water kit, which is why I encourage you to do so. Please watch my my video on testing your home water and make sure that what you are drinking is safe. What you see here is Flint and Detroit's water as comparisons. You see what their pipes used to look like in Flint, Michigan, since they weren't treating it with that anti-corrosive agent we'll talk about next. And you see the bottled water up above, over there we go, the bottled water up above, that they all have colors. This is not from the lead. Again, please keep in mind, lead is invisible when it's in the water. That color is coming from copper. Please recall that it's the lead and copper rule. So there's copper, there's iron, there's other things in our pipes that are giving it that kind of browny, nasty, yucky color, right? But lead itself is invisible. You wouldn't see that with the naked eye, nor taste it, nor smell it. You wouldn't know that it's there. Silent killer, right? So let's jump back to this anti-corrosive agent that they failed to use. First and foremost, what does it mean to be anti-corrosive? Well, basically we need to know what corrosive is and then what the anti is. So for something to be corrosive, it deteriorates, right? Or it begins to fall apart or crumble. So anti that would mean, hey, any measure taken to stop something from deteriorating or crumbling or falling apart. That would be an anti-corrosive agent or anti-corrosion, literally. In other words, anything that would stop the corrosion of metal or the breakdown of metal would be an anti-corrosive agent. And we use chemicals to do that, to prevent corrosion. One of the misconceptions I want to talk about here that I've heard often is that, well, lead is a metal. So metals don't just dissolve in water, Mrs. Duckonta, right? No, I mean, if I took this pair of scissors and I put it in the water, you're absolutely right. It's just food coloring, by the way. It's not really Kool-Aid. No, it's just a couple. So anyways, if I was to do that, this metal is not going to dissolve. You're absolutely right. But if you watch my video on what dissolves what, right? Solubility, my whole little lab tests, you'll note that there are metals that dissolve in some solutions or in some solvents to make a solution. So you do have some metals acting as a solute that can dissolve in certain solvents to make a solution. So just because this metal doesn't dissolve in this solvent doesn't mean that it wouldn't dissolve in a different solvent. As you can see in this GIF over here, that's actually gold dissolving in iodine. So gold itself is a metal, right? You have your nice jewelry made out of it and whatnot, can dissolve in the right solvent if given the chance. So then what would be the right solvent for Flint, Michigan? We need to think in terms of antioxidants and oxidants again. Hopefully you've seen the word antioxidant somewhere, right? So like if you've ever eaten blueberries, like these are my absolute favorite, right? You see this word plastered all over the place. Antioxidants, they're so good for you. Packed with antioxidants. Buy our stuff, right? So if antioxidants are the good thing, right? Or at least what's promoted to be the good thing, then we would assume that oxidants would be the bad thing, right? Or at least we would assume. And the word oxidant kind of hopefully reminds you of the element oxygen. So what we see then is that if we have a solvent with oxidants in them, or like oxygen, for example, we could have a solvent that is corrosive enough to dissolve the solute of lead or metal in this case. That would be the case for Flint, Michigan. So let's take a look at this. Oxidants are what caused this problem. So we had these free radicals, if you will, these oxidants or oxygen molecules. You can see that, I'll try and show you with my pointer here, circled over here. So what we had was oxygen, our O2, reacting with exposed pipeline underground. And now these pipes are made out of lead, remember? And lead is represented by Pb on the periodic table. So when oxygen, our oxidant, reacts with the lead pipe, we end up making lead soluble. We dissolve it into the solution by doing that because this solvent with oxidants is now corrosive. So what they failed to do in Flint, Michigan was be able to add an anti-corrosive agent to stop this from happening. And we're going to talk about how we can stop that from happening as well here in a second. Hang tight. So, as I mentioned, oxygen, very electronegative, very reactive. It's an oxidant, and that is what causes this whole issue to take place. Makes the iron, Fe, and lead in the pipes leach into the water system. Again, notice that in this picture, the lead is invisible, the water's still clear, and the thing that's causing this brown, nasty color is iron within the pipes, not the lead, okay? So again, if you're looking at this picture, real water picture of Flint, Michigan's water, the first bottle is fairly clear. There's probably lead in all of those, and although the one on the end looks the nastiest, truly, right? It's all orange and gross. That one is probably just contaminated with a lot of iron. What we're really, really worried about, not that we're not worried about iron, but worried about the lead, and the lead's invisible. So what we need to do is figure out, how do we get the lead out of the water? How are we going to do that? And I want you to think about it. I have the pause button there because I really do want you to pause the video and I want you to think about it. Based off of what I have told you in this video, if we had soluble lead, i.e. lead that is dissolved, floating around in the water supply, how could you remove it from the water? What would you need to do to remove it? What would you need to add to the water to remove it? Please pause. I'll wait. How could you make the lead insoluble? I'm waiting for your brilliant ideas. I'm so excited. Okay, that's all I can wait. All right. So, how could we make it insoluble? Well, let's see again. What did we see before? This guy's video showed us that, hey, and I'm going to play it, but actually put it on mute here. So this guy was showing us that, hey, we've got this clear solution of lead. That's what the aqueous means, by the way. It's a solution of lead. So we have lead in there. Looks like any normal water, like the water in here. And that's soluble lead. That's lead that's dissolved in a solution, a solute mixed with a solvent, making a lead solution. Now he adds a different chemical. Boom! All of a sudden we have lead coming out of the solution. So lead has now been made insoluble. It's now a solid. If that's a solid, are you going to drink that in your water? Do you have to run the risk of consuming it if there's a whole solid layer? No, you don't, because it's out of the water. When you precipitate it out, it is literally removed from the water source. So what we see then is that Flint, Michigan failed to add an anti-corrosive agent that would cause lead to precipitate out of the solution. This would have fixed all of the problems. Just let that sink in for a second. Also, what could fix Newark, New Jersey? Adding the correct amount of anti-corrosive agent. Check out these pipes. So the first pipe, obviously not treated. It's very corroded. So you've got a lead pipe that's just got all of this buildup, all this gunk, this lead and this iron and whatever else is in there is leached into the water supply. Whereas if you look all the way over there, we've got treated with phosphate. We're going to talk about that in a second. Phosphate is the anti-corrosive agent. That's a chemical they could add to the water that would bind up the lead that's floating around and make it drop to the bottom. So if you see this kind of white layer, that's literally the insoluble solid precipitate that has lead in it. It can't dissolve back into the water because it's bound up as a solid, like a rock, right? Like rocks are solid. So it wouldn't be in the water anymore to drink. Pretty simple solution. And actually rather inexpensive as well to fix. Alrighty, so some chemicals that make lead insoluble. That's PB again, lead. So what they would have wanted to add is this thing called orthophosphate. That's PO4. And that's right here. So there's P and there's 4 O's. That's PO4. That is the phosphate anti-corrosive agent. This would have stopped oxygen from being able to reach the metal pipe. If you remember, it was because it was exposed. But if we add this to it, what we then see is that it makes a solid layer that protects and coats the inside of the pipe so that any oxidants or free radicals within the water can't react or even reach the lead piping. Pretty simple fix, right? So all it would have taken is the right amount of orthophosphate. Overall lesson here that I want you guys to take away from this is go ducking test your water. Please go home, ducking test your water. It's important. Your life and the lives of your loved ones could depend on it. Anyways, this is Duckonta. Hope you enjoyed this session. I ducking love science and I hope you do too. Thanks. Bye.